Equation of a tangent to y equals 2 on x squared at x is minus 1 and y is 2. Alright, and I'm going to bring my Vivi up here and all that as well, because I might do some graphing. Vivi. And remind me to talk about holiday tutorials today as well. Okay, let's go to demos. Let's just sketch the function to begin with, and then we can look at what the tangent means in the context of it. Hey, Austin. So the function is 2 on top of x squared. Very good. Okay, the tangent at x is minus 1. So to find the tangent, we need two things. Okay, we need the point of contact and we need the slope. Okay, we're given the point of contact. Okay, we're given both the x coordinate and the y coordinate. So that's all good. To find the slope, we need to use the derivative function. Okay, so we have y is 2 on x squared, which is 2x to the minus 2. Which means dy on dx is going to be minus 4x to the minus 3, which is minus 4 on x to the power of 3. Okay. Now we've got when x is minus 1, dy on dx will be minus 4 on top of minus 1 to the power of 3. Now a negative to the power of an odd number will always be negative. You can think of it as minus 1 times minus 1 becomes positive 1, and then times minus 1 makes the whole thing negative. Okay? So when there's odd, there's always an odd amount of negatives, which makes the whole thing negative. So we've got minus 4 on minus 1, which is positive 4. We've got our slope. We've got everything we need for a tangent. What is a tangent? It's a line with these properties. It's the equation of a line, touches there, and has this slope. From here, we have three processes we can do. We can just find the equation of a line, we can use the formula, or we can even do the formula in general form. I'm just going to use a bit of an intuitive process here because I think it makes more sense to understand what we're doing when we find a tangent. A tangent is a line that is parallel to the curve. So we're going y equals mx plus c. That's the equation of a line. Our slope is positive 4. So we've got y equals 4x plus c. Our point of contact is minus 1 and 2. That means when x is minus 1, y is 2. So we're going to substitute that information into this statement. C is positive 6, and therefore the equation of the tangent is 4x plus 6. Okay, let me give a quick sketch of that one. Beautiful tangent there, parallel to the curve, at x is minus 1. Okay? We also do the general form process. Should we do it or just move on? Let's do it. Let's do the general form process. So remember in general form, let me make this statement up here. If you have slope a on b, then you're going to write it as ax take by equals c. And if you have slope minus a on b, then you're going to write it as ax plus by equals c. Now, I think I might have written that information. That's it, where it says general form here on the tangent. That's all written there. Okay, so let's look. We've got a slope of 4, which as a fraction is 4 on top of 1. Okay, so we're going, is it positive or negative? It's positive, which means we're going to write it out like this. Okay, it is going to be 4x take 1y equals c. Okay, I've just gone straight from positive slope to this statement, and then all you have to do is substitute in the point of contact. So we're going to have 4 times minus 1, take 1 times positive 2. And we've got minus 4 take 2, we've got minus 6. And so then the equation in general form is 4x take y is minus 6. Okay, I'll sketch that up here. Okay, it's the exact same line. All right, and you can see the relationship pretty clearly between these two anyway. All right, all they've done is move the 4x over this side and divided both sides by -1. You can see how close they are.
Is it better to just make it into y-intercept and do it that way?
You could do it. You can absolutely do that if you're required to answer in general form. 95% of the time, in all the questions I've seen, it doesn't specify a procedure it wants you to follow. It just says find the tangent. Both are useful. I think y-intercept is more useful because it shows you the slope and it shows you the y-intercept.
Can't we use the tangent formula?
You can, yep. And if you do, it will generate this solution.
Yep.
What's the tangent?
Yep. Very good. Okay, let's move on then. So maybe you remember when we did exercises 3B, 3C, and 3D, they all culminated in exercise 3D, which was a good point of reflection on all of the previous things about it, about how we can use the first derivative and the second derivative to answer these properties about the function. So we've got f of x equals x to the 3 take 3x squared. Okay, part A. Find when f of x is increasing and decreasing. Well, let's sketch this one, because the very first thing to do, like in order to answer this is where you could just look at your calculator. You could just look at the graph. So it's x to the 3 take 3x squared. Okay, you could just look at the graph, and from the graph, like if you follow my mouse along here, you can see it's increasing until we get to x is 0, and then decreasing from 0 to 2, and then increasing for values after 2. All right? So you could just answer that from the graph. In the test, however, we say, using calculus methods, find points when it's increasing and decreasing. So we can't just refer straight to our calculator. In the exam, more often than not, they don't tell you a procedure to follow. They just say, state this, find this. So you can use a calculator. We can use calculus methods. If it wants you to use a procedure, it will be very explicit. Okay, so if we want to find when it's increasing and decreasing, our procedure there is to differentiate, so find the derivative, and then draw the sine diagram of the derivative function, because that's going to tell us when it has positive slope and when it has negative slope. So if we're thinking about drawing the sine diagram, I'm going to do it manually, okay? But again, you could rely on your calculator at this part. We want the sine diagram of this function. I'm going to go, okay, I need to find the roots, because a sine diagram tells you where it equals 0. So I need to find the roots. So if I make that equal to 0, we can factorise 3x out the front, and we're left with x take 2 in brackets. And so we've got these two solutions, x is 0 or x is 2. All right. The other thing is that it's a quadratic and it has a positive a value. A is larger than 0, which means it's opening upwards. Remember, if a is positive, it's going to be positive, smiley face. And so it's going to have this shape on our graph. Okay, and so we've drawn the sine diagram of f dash of x. Okay, so if you're unsure how I generated that, all right, if you're worried about that part, that's where you can go straight to your calculator and graph the derivative function. Okay, I'll just turn the purple one off. And you're just drawing the sine diagram of this function. Okay, above the x-axis until 0, below the x-axis between 0 and 2, and then above. So that's another way you can generate that same solution. Okay, and then this is the slope function. And what is increasing and decreasing but a statement of when it has positive slope and a statement of when it has negative slope? That's what this sine diagram tells us. We have positive slope for values less than 0 and greater than 2. That means it's increasing over those intervals. So let's make a statement. If f of x is increasing for x is less than or equal to 0 and x is greater than or equal to 2. We always include the point unless there's an asymptote. Okay, so the black function, so let's talk about those relationships because this pops up in in 3D.2, the relationships, and these are quite difficult to wrap our head around. But what we can see from the black function, okay, that is the derivative function, and then we have the purple function, which is the original function. Now we're asking the question is, when is the original function increasing and decreasing? Okay, the black function is the slope. So what we can see is the black function is above the x-axis until we get to 0. Okay, so that means the original function, f of x, has positive slope, that is, it is increasing until we get to 0. Alright, it gets to 0. And then the black function is below the x-axis. Okay, it's below the x-axis between 0 and 2, which means it has negative slope between 0 and 2. And of course you see that between 0 and 2, you're walking downhill. Okay, it's going down. You've got negative slope until you get to this point where the slope function is now above the x-axis. Okay, which means the original function has positive slope, and so now we will be walking up the positive slope function there. Alright, so they're the relationships that you're pointing out here. What's the process? Find the derivative, draw the sine diagram, and then when the sine diagram is positive, it's increasing. When the sine diagram is negative, it's decreasing. Okay, what's it say next? Find coordinates, stationary points. Okay, so stationary points are things like local max and local min. We can see we've got a local max at x is 0 and a local min at x is 2. And then whatever that y value is. To find the y value, you need to put it back into the original function. Okay, how else could you do that? G solve max, G solve min. Okay, so they're just getting you to use calculus methods. This is how we use calculus methods, is the f dash of x. So use your calculator to help you, use it to check your answers. Alright, find when it's concave up and concave down. So for this, we need to draw the sine diagram of the second derivative. So if this is f dash of x, let's make that statement here, f dash of x is 3x squared take 6x. That means f double dash of x will be 6x take 6. It's the equation of a line. It has positive slope. Okay, so already we're thinking of the sine diagram. We've got positive slope, equation of a line. We just need to know the value of x that makes it 0. Okay, you put the number, okay, you can solve it. 6x take 6 is 0, 6x is 6, x is 1. Okay, so that's the value that makes it equal to 0, and it has positive slope, which means it's going from negative to positive. Okay, so then this is the sine diagram of the second derivative. And so we have concave down when the second derivative is negative, and concave up when the second derivative is positive. Okay, which means we have a point of inflection at x is 1. Okay, that's where it transitions from being concave up to concave down. So a non-stationary point of inflection. So if x is 1, then y is going to be minus 2. Right, and so we can observe that on our graph. Okay, so the point of inflection is here. At x is 1. You can see, like I'm tracing along it, it's concave down until we get to positive 1, and then it transitions to be concave up. All right, so we can get that using calculus methods. What else we should notice is that that point of inflection, the point of inflection on f of x, corresponds with the turning point on f dash of x, okay? That f dash of x has a local min when f of x has a point of inflection. And then if I'm to graph the second derivative, we're going to have 6x take 6, okay? Corresponds with a root. Look at this, there's the root, there's the turning point, and then there's the point of inflection. At x is 1, y is minus 2. So they all correspond with one another. The same x values, different y values. If you want to know the y value, you need to put the x value into the original function. Okay, so there's our first two. Right, spin the board around. Prepared. Any questions at this stage? We're sort of remembering it. Okay, kinematics. So this is describing motion, and we have the displacement is 12t. Take 2t to the 3, take 1. Find v of t and a of t. So v of t is the first derivative, and a of t is going to be the second derivative. Yep, that's all good. Find the initial conditions. So that means the initial displacement, initial velocity, initial acceleration. So let's do that up here. S of 0 is going to be -1. V of 0 is going to be 12. And A of 0 is going to be 0. Okay, so what does it mean? Initially, what's our context? The particle is 1 unit to the left, moving 12 units per period of time, per second, to the right, okay? And it's not accelerating. That would be a statement we could make there. Find the time when it changes direction. So it changes direction when the velocity changes from positive to negative. So let's draw the sine diagram of the velocity function. So I'm looking at that and going, that's a quadratic. Okay, so we could rely on our calculator and go, graph that in our calculator and get the sine diagram from there. Let's do it manually again. Let's try and do these things manually if we can. We've got 6t squared is 12. Divide both sides by 6. You've got t squared is 6, is 2. And you've got t is plus or minus the square root of 2. Okay? So what that means, if you were to draw the velocity sine diagram, okay, this is the sine diagram of v of t. It has a root at positive root 2 and at negative root 2, but we don't consider negative values of time. So we're not interested in this one over here. All right? And then I'd be looking at it, I'm going, it's a quadratic. The a value, so that's the coefficient of the squared term, is negative. A is negative, it's -6, which means it's opening downwards. It's a sad face, it's negative, it's going to be sad, it's negative all the time. So that means, if this was the other root, you can imagine it's going to have this shape, which means it's going to go from positive to negative. And we can verify on our graph. Okay, so let's graph the derivative function here. It's going to be 12 take 6x squared. Okay, look at that. That's the graph of it. Okay, opening downwards, and the root is 1.4. Okay, square root of 2. All right, so that's the sine diagram of the velocity function. Find the time and position when it reverses direction. So it reverses direction when t equals the square root of pi, square root of 2. What's happening is this particle is moving to the right, and then it starts moving to the left. Okay, it has positive velocity moving right, negative velocity moving left. So that's when it changes direction. We want to know the position, which means we need the displacement. We need the displacement when time is root 2. Okay, which means we put this into the original function. So to do that, I'm just going to use the calculator here. So that's going to be 12x take 2x to the 3 take 1. Turn a few functions up here. And I want to know what's the y value when x is the square root of 2. Okay, so if you put root 2 into the equation, it's going to be a nasty number as well. 9.899. So we'll just round that to 3 significant figures. We'll just go up to 9.9. All right, so we've got the displacement, the time and position when it changes direction. That's part C. Done. Part D. When is the speed increasing and when is the velocity increasing? Okay, to answer this, we need to compare the velocity sign diagram with the acceleration diagram. Okay? Now the acceleration diagram is the equation of a line with a negative slope. Okay, which means it's always going down, which means the acceleration is always negative. Okay? So speed increases when these have the same sign. I'll check that summary sheet. Speed increases when they have the same sign. An object's speed is magnitude of velocity. If v of t and a of t have the same sign, then speed is increasing. If they have opposite signs, then speed is decreasing. Very good. Okay, so first part says, when is the speed increasing? Well, the speed is increasing when they have the same sign, when they're both negative. So that's going to be when t is greater than or equal to the square root of 2 seconds. Okay, that's when the speed is going to increase. What that means is it's moving in a negative direction and getting faster in a negative direction. Okay? What about when the velocity is increasing? For velocity to increase, then both speed and velocity need to be positive. Okay? That does not occur anywhere, so therefore never. Never. Velocity is never increasing. Okay. Draw a motion diagram. So what we have is our axes. Here's s of here's 0. It starts at -1 and it's initially moving to the right until it gets to 9.9 meters. All right, so that can be there, 9.9 meters when t is the square root of 2, and then it moves in the opposite direction.
I didn't understand the speed increasing and decreasing. I get that it's increasing in the same, and the sign's same, but what do you mean by velocity is never increasing?
So velocity will only increase if they're both positive, and then they're never both positive.
So what was the first one?
Increasing when they have the same sign.
Yeah.
Yep. So there they have the same sign when for values larger than root 2. And here it's going to be velocity is increasing when acceleration and velocity are both positive.
Yeah. Okay.
Yeah. Which is never. Cool. Okay. So motion diagram done. We're on to F. The rate of trees. Okay, so we have the height of Pinus radiata. That's what we're growing in the amount here. H is 20, take 97.5 on t plus 5. Okay. Part A. Find how high the tree was when it was planted. So that means when time is 0. So h of 0 is going to be 20, take 97.5 divided by 5. We can solve that. .5 meters, 50 centimeters initially. All right, next part. How high is it after 4 years, 8 years, 12 years? Okay, so that's just where you put the number 4, 8, and 12 into here. So you find h of 4, h of 8, h of 12. I think we can move on from that. H of 4, h of 8. Okay, part C. Find the rate at which the tree is growing after 0 years, 5 years, and 10 years. Well, what is the rate of change but the derivative function? So we need to find the derivative and then we put those time values into the derivative function. So if this is our function, okay, I'm going to express it like this first. It's 20, take 97.5 times t plus 5 to the power of minus 1. Okay, so I'm bringing it to the top there. That's a 7. Okay, and then we're ready to differentiate. This is just going to disappear, so I'm just going to call it h dash. 20 disappears, the minus 97.5 is just going to hang out, and then we're just chaining them. Okay, it is f of x to the power of n. So it's going to become n f of x. Alright, so n f of x to the n take 1 times by f dash of x. The derivative of the inside here is 1. Alright, so that's a chain rule. Okay, function to the power of n f of x, n take 1 times f dash of x, the derivative of that. Okay, so we'll just simplify that a bit. We've got two negatives, so it's going to be positive, 97.5 on top of t plus 5 squared. That's going to be the rate of change for any value of time. Okay, so that means we can, we're asked what is the rate of change when the time is 0, when the time is 5. So let's find h dash of 5. Okay, so after 5 years, how fast is it growing? It's growing at 97.5 divided by 5 plus 5 squared. So that 97.5 on 100 is 0.975 meters per year. Okay, so we have height is in meters and the time period is in years. Alright, and then for the last part, show that the rate of change is always positive. Okay, so we've got as t approaches infinity, okay, as t gets really large, what we've got is we've got positive 97.5 divided by some massive number. Okay, so as t approaches infinity, dh on dt, I think you like it, is approaching 0 from the positive side. Alright, and so what that's saying is if you graph the derivative function, I'm not exactly sure what the primary shape it's going to look like, but it's going to be something like this. It's going to get closer and closer and closer to the x-axis. Alright, but the point is it's always positive. The rate of change is always positive. What's the significance of it? The tree is always growing. It's never shrinking. Okay, or it's never, it doesn't have a negative growth. What I want to say about this one, okay, is you should remember as well, if you graph this on your calculator, if you have the setting turned on, when you g-solve, let's say you g-solve when x is 4, it can tell you the height and the rate of change at that point. There's a part that says y, and there's a part that says dy and dx equals. That tells you the slope and the height at that point. So use both of them. Okay, last one. Unless there's any questions about that.
What does that superscript plus mean?
It just means it's approaching 0 from the positive side.
Okay.
Yep.
Can we still say infinity?
So time is approaching infinity. The rate of change is not approaching infinity because what's going on is this part's approaching infinity, and so you've got a positive number divided by positive infinity, which is, it's going to be really small, but it's still going to be positive.
So you don't have to prove that.
Yeah, it just means make a statement like this.
Oh, alright,
Yeah.
cool.
Yeah. You could break it down a little bit more. I mean, do you want me to show you?
Would you just do it as like
Yep.
h of like 909 billion and then just show that it's like...
So like making an inductive case. So if you were to break it down, okay, what you have, t plus 5 squared. So as t approaches infinity, okay, t plus 5 squared approaches infinity, all right? And so then 1 on t plus 5 squared approaches 0 from the positive side, and so therefore 97.5 times 1 on t plus 5 squared approaches 0 from the positive side. Okay, so we've got this is going to infinity, therefore this is going to 0, therefore anything times 0 is also going to 0, but it's still positive.
So if we graph it on our calculator, we'll see that the 0 is the asymptote.
Yeah,
and
absolutely.
It'll get really close.
Yes, yeah. And remember on your calculator as well, you've got the function, you can make your calculator graph the derivative for you as well, even if you haven't solved it properly. Okay? Alright, we've got a 2 litre box. Alright, last one, good. We've got a 2 litre box. And it's got a square base, and these have a height of y. Okay, part A. Explain why y equals 2000 on x squared.
Just does.
Okay, so, well, the volume of this box is going to equal x squared times y. It's the base times the height. Alright? Now the volume is 2 litres or 2000 centimetres cubed. Okay, that's the initial statement. And then divide both sides by x squared. We've got y is 2000 on x squared. Okay. So that's part A. Part B. Show that the surface area is given by this equation. It has an open top, so we don't include the top. So when we're talking about surface area, okay, we need the bottom, okay, and the bottom is going to be, so I'm going to make an argument like this. The bottom is going to be x squared, and then there's 4 walls. There's 4 of them, and each wall has an area of x times y. Okay, so that means the surface area is equation of A is x squared plus 4xy, but y is 2000 on x squared. So we plug that in. Okay, good. That's part B. Part C, find the dimensions of the box which minimise its surface area. So optimisation. Okay, so a couple of ways you could solve this. We want, here's the surface area function. We want to know when it's minimised. Graph G solve min. Okay, that's going to be your solution. But let's use some calculus methods. So what we need to do, we want to know when maximum and minimum occurs, when the first derivative equals 0. So we need to find a dash of x. So firstly, let's write a of x in a form ready to differentiate. And then we'll find a dash. Okay, we want to know when the first derivative is equal to 0. That's how we draw its sine diagram, isn't it? So if it equals 0, I'm going to multiply both sides by x squared. So we're going to have 2x to the 3, take 8,000 is 0, and then we can solve that pretty easily. So it's 15.87. Okay, so the minimum surface area, so that's when we're using the least amount of materials to be the most efficient, occurs when x is 15.9. Alright, so that's the minimum solution. Hence, find the minimum surface area. So that means, what is the area when x is 15.9? So that's putting 15.9 into the original function. Now, if you graph this one, and G solve the min, or this function here, like I said, G solve the min, it's going to tell you that x value, and it's going to tell you the area value at the same time. Okay, because on the x-axis you have the value of x, And on the y-axis, you've got the value of the area. That's what's on the y-axis for this function. Cool. So, let's do some of chapter 3.